All right, so exam 2 is over chapter 20 and only chapter 20 in regards to the logistics similar to the first exam, meaning it is roughly 1/3 multiple choice, at least by points, and then 2/3 by points calculation questions, meaning the ones where you can get partial credit. And the multiple choice will be more on the concepts, and then the calculation will be more on actually using those to calculate things. You can bring a cheat sheet with whatever you want on it on one side of a sheet of paper, 8.5 by 11, and I think that's the main things. So I'm just going to jump into what is important from this chapter or what I will be testing on. You don't need to know, at least you won't be tested on the difference between moving charge in circuits and static charge, what we were doing prior to this chapter. But this analogy may help you see how these things are connected. So not tested on, but just may help give you a better mental picture. What can be tested on is either how to calculate current or knowing about conventional current. Conventional current is we got sick of looking at what negative charges do and realizing they always do the opposite of what we'd like them to. So we decided to just pretending it's positive charge. You have to ask the question, okay, how should positive charge move in order to do the same thing that the actual negative charge, the electrons in the wires, do? And the answer is conventional or positive charge current would have to move the exact opposite direction of the electrons. So conventional current is positive charge flowing opposite the direction the actual negatively charged electrons move in the circuit. And we use it to just make our life easier and finally have these things make a little bit more sense and not have to do it all backwards. There won't be, again, direct questions on EMF, because you can essentially think of it as the voltage of the battery. They're slightly different, and it is sort of a subtle difference, but the EMF is the work the battery is doing to give something energy, and then the voltage is the difference in energy as either charge gains it or loses it. Both are on a per charge basis, meaning you're describing how much energy is given to or taken from each charge, each coulomb of charge at least. And so that's why the units of volts are joules per coulomb. It is the amount of energy given or taken per coulomb of charge. This, again, is just good as a mental picture, but not tested on. We will assume all batteries are ideal, so you don't have to worry about internal resistance in this exam. I won't make you calculate anything with this temperature dependence for resistivity. I will just give you a value for resistivity in a problem where you might have to calculate the resistance, something like this equation on the next page. I could ask for this temperature stuff, just what effect does it have on resistivity? The effect it has is, at least for all the materials we've looked at, it increases resistivity if the temperature goes up. So as you heat things up, they become more resistive to the motion of charge. I can test on this primarily through calculations, that there is this relationship between resistance, voltage, and current. It's actually how we define resistance in the first place. But there is separately the statement Ohm's law, which is that number R doesn't change even when I change the voltage or the current. So to give an example, I connect a 1.5 volt battery up to a wire, and that wire, we see a current of 1 amp flow. We could take those two measurements, divide them to realize, okay, 1.5 volts over 1 amp, that's 1.5 ohms for the resistance. That's the definition of it. Ohm's law would say, all right, well, now I put two batteries in. I've got 3 volts. What happens to the current? It is 2 amps now. So what is the resistance? Still 1.5 ohms. It hasn't changed. That's Ohm's law. Both of these calculations are the type you could expect to see, but possibly mashed together. So I could tell you, say, here's a voltage, and here's the current that results, and here's some details about this piece of wire I was using. You tell me what the resistivity of the wire is, you could calculate it from this, Or I give you that and you tell me what the length of the wire is. Or I give you those and you tell me what the area of the wire is. Just whatever question, it's just variations on that question. P equals IV. That is the relationship between power, the amount of energy transferred per second, and current and voltage. It's a general relationship for any electronic device whatsoever. For resistors, though, it has these special values, V squared over R and I squared R. So you can use any of those three and you should get the same answer for a resistor. If you don't, that means you used the wrong value for either I or V. And that's really easy to do when we get into the circuits because there's lots of I's and V's flying around. You got to make sure for the resistor you're interested in, you're looking at the voltage specifically across it, the current specifically through it. This equation, or these three equations, are only valid for those voltages and currents. Kirchhoff's rules, I'll come back to when we actually get to the calculation because that's where they become important. Here we just used them to get these features of resistors in series. The stuff in the box is the important part, and same for resistors in parallel. So those properties of resistors in series and parallel are the important bits. The rest was just deriving that stuff. This problem is good to look back at, because for one, it shows you that thing I was talking about of you got to have the right voltage and current, or you won't get the right power values. And then, let's see, this page was just an add-on to talk about how you can tell if something's in series or parallel. You got the pinch test, which is just, can you put your fingers on both sides of one of the resistors, thumbs on both sides of the other, and when you slide your fingers and thumbs along the wire, can you get them to meet at a junction without running into anything else first? For instance, a battery or another resistor or a capacitor, just something that's not one of those two resistors. The other test, the one for series, is can you put your finger on one, slide to the other, and not run into anything at all in between, not even a junction. You can't run into anything in between. You have to have a direct path from one to the other and no choices in between. So if there were a wire coming off right here and connected in some other way to something else, you would say those are not in series because something gets in the way. This question is going to be the most bang for your buck of what you can expect on the exam for resistors. It asks all the main things about them except for maybe the power dissipated. All you have to do to find that is take the I's and V's that we found and multiply them together, or use V squared over R, or I squared R, doesn't matter because we found every value in this problem. So this one is very important to look at. For Kirchhoff's rules, I said I'm not going to expect you to solve the equations, just be able to set them up. So you got to be able to do this part. Set up your three equations, one for a junction and then two for loops, and that's it. And in the problem, or on the exam, I've gotten questions about like, well, you said it doesn't matter which way we draw the currents, right? If I had drawn them some other way, it'll still work out, I'd just get negative values, but how can that be on the exam? It'll either be that I give you some currents, I pick for you, and you just have to tell me based on those what is the equation, or I still let you pick, and I just grade based on your pick. Does your equation agree with the pick you made? I haven't decided which one I want to do yet. And I've been asked about some examples on Kirchhoff's rules, so we'll see this in action in a little bit. All right, capacitors. It's the same thing as resistors. It's just the roles swap. So equivalent capacitance for series is the complicated one, whereas for resistors, series is the easy one where you just add. Capacitors in parallel is the easy one. You just add. But resistors in parallel, it's the complicated reciprocal thing, which I'm realizing I never wrote C parallel equals C1 plus C2 here. We found it up above, but I didn't write it in this box. My bad. That does not mean the stuff up here changes. So it's still true whether you're talking about resistors or capacitors in parallel, that the voltage is the same across them. And then for resistors or capacitors in parallel, the charge or current is split. And we come back to series. Doesn't matter whether we're talking about resistors or capacitors. In series, they split the voltage and share the charge, have the same charge or same current in common. This is doing the same thing as with the resistors, but for capacitors. And you just have to remember that your rule here is not V equals IR, it's Q equals CV. And then that the roles of capacitance swap, how you combine capacitors. For RC circuits, I will not ask you to do stuff with the exponential. The main things I'm asking you to remember about capacitors in RC circuits is the qualitative stuff. So conceptual type stuff. Any calculations I ask you to do would be things like, okay, what is the full charge that accumulates? That's just the capacitance of your capacitor, the size of your water tower, times the voltage, how strong your pump is, the battery voltage. That's the most charge you can accumulate. Or I could ask you how long that takes. It takes 5 time constants. What's a time constant? The time to reach 63% of full charge, and it can be calculated with resistance times capacitance. So 5 RCs. That's how long it takes to fully charge up your capacitor or to fully discharge it. Also takes that long for a discharge. So I'm not making you do like at a specific time how much charge is there. To do that, you'd have to sub in here and do some exponentials and all that stuff. I'm not asking for that. I'm asking for concepts and those easier calculations, such as that one right there. And that's it. The rest is not tested on. I'm not testing on electrical safety. I don't know how I would do that on an exam anyway. I did get a decent number of questions emailed in, so I'm just going to start going through. The first couple were from the homework. So this question is a Kirchhoff's rules question. None of the resistors in the circuit shown are connected in series or parallel. We want to find the current I5 and the resistance R2 and R3. All right, so if we want to, we can label every junction in this, which I see 4 of them. They put dots there to help us see them, but there are 4 junctions in this circuit, and we can set up the junction rule at every one of them. I'll go ahead and do that just to see what it would look like, but there's an easier way. It actually is the junction rule, but just sidestepping some stuff. So it doesn't tell me how much current the battery provides in this circuit, but I'll just call that, let's say, I1. And then it doesn't tell me how much current goes through resistor 4, so I'll just call that I4. I don't know that current flows the way I'm drawing it right now. I'm just guessing. But based on that guess, I would say at this junction, because I know 12 amps left it from up here, that what goes in, I1, equals what comes out. 12 amps plus 9 amps. So 21 amps. All right, I keep going. I could look at this junction. I5 goes in, 6 amps goes in, I1 comes out. 6 amps plus I5 equals 21 amps. That means I5 must equal 15 amps. I'm done with part A. But I can keep going. All right, 9 amps comes in, and I see 6 amps goes out to the right, and I4 goes out through the bottom. So my rule for that junction, talking about this one right here, is 9 in equals I4 plus 6 amps. So I4 is 3 amps. And then finally this junction down here, I see that 3 amps, or we'll, I guess just still call it I4, goes in here. I5 comes out that way. And then if I realize this is up here, that must eventually snake around the 12 amps and enter. So I have the equation I4 plus 12 amps is what goes in, equals I5. That's what comes out. If I know that I4 is 3 amps from that previous junction, this is another way I could find that I5 is 12 amps. I'm sorry, 15 amps. Okay, so that's just applying the junction rule at every junction in the circuit. Now, the easier way is to just recognize how these currents are flowing through the circuit. It is the junction rule, but it's just doing it without writing out equations. So if I see that 9 amps goes into this junction and 6 amps came out one way, whatever's left over has to come out the other way. It's like if you saw 100 people walk into this room and 50 walked out to the right, 50 must have walked downward too, unless they're all just congregating in this room. You're not allowed to do that at a junction because we set up this steady state current. If I saw 100 people walk in and 70 people walk out to the right, 30 are walking down. It's the same math. All right, so 3 amps we found comes out of this junction, and so 3 amps goes in down here. We already knew 12 amps came in down here. Well, 3 amps go in, 12 amps goes in. They're asking what comes out. If 3 people walk into the room from one side, 12 walk in from the other side, how many walk out of the room? 15. All right, so I'm just going to note that I4 we found was 3 amps, I5 is 15 amps. And then the question for B and C is what are R2 and R3? So for this, if they're asking about resistances, that doesn't show up in the junction rule. It's only about currents. So if I want to find these resistances, I got to move on to the loop rule. Identify all the loops in my circuit. I see there are 3 kind of obvious ones. There's others that we could get from combining these 3, but I only need 2 equations to be able to find B and C. So I'll just look at these 3 loops and see which ones are going to be most helpful for that. If I use this loop up here, I'll call it loop 1, it could help me find R2 because that's included in the loop. If I use the bottom left one, that could help me find R2 as well. If I use the right one, that can help me find R3. So I might go with, let's say loop 2 and loop 3. I don't really have a reason for that, but I'm just going to go with those 2. And I'm just going to report rises and drops. So I need to follow Kirchhoff's rules pretty closely here. I would recommend, if we come back to the notes, that when you're doing these problems with Kirchhoff's rules, have this in front of you, because you'll think you're following the steps, but you're missing something, you're skipping something, and then it becomes confusing and you're not sure where you got lost. So if you follow these steps to a T, it should work out unless you missed something. So what we've done so far is we set up the junction rule by labeling currents. It said it doesn't actually matter how we label them. If we labeled wrong, we'll get some negative values. And then current leaving one junction enters another. That was the thing where I was saying, okay, well 12 amps comes out right here. It must go in at some other junction because we just follow it around a branch. All right, now we're at step 2. We need to label the resistor terminals based on the current directions. So let me come back to the problem. For some of these, I've already got the currents labeled. Let me add back in how I had drawn I4. And then call this maybe I1. So based on that, I want current to flow from high to low through each resistor, meaning positive to negative. So the 9 amps flows to the left. That's why I used positive and then negative, right to left. And I4 flows down. I5 flows up. So for positive to negative on that one, the positive has to be the bottom terminal. And for R3, we've got 12 amps flowing down through it. And for R2, I have 6 amps flowing left to right, plus to minus. All right, that's step 2 done. Step 3, set up the loop rule by traveling clockwise around each loop in the circuit. No matter what I see, if I walk from negative to positive, I call it a rise, positive to negative is a drop, and then the next bit, use IR if I run into a resistor, because that's how I get the voltage across it. All right, so I decided to do loop 2 and loop 3. I'll start from the bottom left corner. No reason for that. You can start anywhere you want. I just like to do that. My brain prefers it for some reason. So I'm going to walk clockwise, follow the loop. The thing I see first is the negative terminal of R4 and then the positive. So that's a rise of I4, R4. The next thing I see is R2. I see the positive terminal of it first and then the negative, so that's a drop of, we could call it I2, R2, which is what I was about to do, but we're given this current. So I'll go ahead and say 6 amps R2. And next I see R5. I'm going to go from negative to positive, so I would call that a rise of I5, R5. I could put 15 amps in for I5, but I'll just sub it in a minute. And I'm done walking around that loop. That's everything I've seen. All right, now for loop 3, I do the same thing. I start maybe at the bottom left corner and work my way around. First, I see the positive terminal of R5 and then the negative, so I drop by I5, R5. Notice what was a rise up here became a drop over here because we're going the other way through R5 in this loop. Next, we see a battery, and we go from its negative to its positive terminal. That's a rise. So that's 75 volts. It's already in volts. We don't need IR. Next, I see R3. I see its positive terminal and then its negative, so that's a drop of I3, which in this case is 12 amps, R3. And I see that I have equations for R2 and R3. I just need every other value. R5 is 2.2 ohms. I5 is 15 amps. I4 is 3 amps. R4 is 2 ohms. So let's see. From loop 2, our equation is 6 plus I5 is 15. R5 is 2.2 equals 6 times R2. And then for loop 3, our equation is 75 equals 15, that's I5, times R5 is 2.2, plus 12 R3. If we solve those, we should get our values for R2 and R3, but I'll just leave it at that, because you don't have to solve, you just have to be able to set these up. That's some loop and junction stuff. The other question was on equivalent capacitance. So I do this in pairs of 2, sometimes 3 if I can get away with it, but I do that and redraw, and then do it again and redraw, and do it again and redraw. The part people always forget is the redraw part. You want to do it all at once, and you get it wrong. If you redraw after every step, it's harder to get it wrong. So I look at this circuit and try and identify series or parallel. A mistake I see a lot is calling these series. They're not, because I can't slide my finger from one to the other without hitting this junction. So that is not series. You might call this parallel. You might think it is. It's still not. I can't put my fingers on this one, my thumbs on this one, and hope to pinch both together, because as I slide my fingers around the wire and my thumbs, I can run into a junction. That's okay for parallel, but I hit another capacitor on both sides, so they're not in parallel. What is true in this circuit is I can slide my finger from the 24 microfarad to the 12 to the 8 with no trouble. That means those are in series. Capacitors in series, I add reciprocals and do 1 over. So 1 over 24 plus 1 over 8 plus 1 over 12. And it's 1 over all of that. People forget that a lot too, of doing that extra 1 over. Should be 4 ohms. 4 ohms, no, 4 microfarads. And now I redraw. So I got A, capacitor, capacitor, B, capacitor. And then I can replace all of these three. I can imagine just taking all that, cutting it right here, and replacing with one single capacitor with a value of 4 microfarads. This is also 4. This is 6, 5. And now I stop and evaluate again. 5, 4, and 6 are not in series, again, because I see this junction in the way. I can't slide my finger from one to the other without running into something. 4 and 4 are in parallel, though, because I can do the pinch on those, and the only thing in between my finger and thumb is a junction. Capacitors in parallel add. So that is 8. And so I can replace both of those with one singular one. This is 5. This is 8. This is 6. And I stop and look at this one, and I see, oh, these are all in series. I can easily get from one to the other, just sliding my finger along. All right, so I can replace those with a single one for capacitors in series, 1 over, 1 over. Comes out to 2-ish. Okay, seems reasonable. All right, so that's that one. I will jump over to some questions from the practice exam. These will go a little quicker because I can have the solutions in front of me and just explain in more detail. So questions I got on this were about 10 as the first question. The question was, what is the total power dissipated by these 3 resistors in series? I could either do that by combining them, adding up all the resistances, and saying how much power is dissipated by that equivalent resistor. That would be the current through it, which we can find is 0.33 amps, because it's 12 volts over this equivalent resistance, and multiply that by the voltage across that one, which is 12 volts. That's one way to get 4 watts. Alternatively, I could find the power dissipated by each individual resistor. To do that, I'm going to need to know either the current through or the voltage across, or both for each resistor. It's easiest to go with the current through because I know that's the same for resistors in series, and so I don't have to do as much work that way. But I can use voltage, like it says here, and separately find the voltage across each because that splits for resistors in series. And then separately calculate IV, or V squared over R, for each resistor and add them all up. So this looks like I'm writing a lot, not because it's a hard problem, but because I'm showing you all the options, or at least most of them. Okay, 12. Same deal here. So what is the equivalent resistance? We've got resistors in parallel. In parallel, it's 1 over, 1 over, the reciprocal stuff. And that is, I guess, all I can really say about it. It's just for in parallel, we did that analysis to say they have the same voltage across them, and they split the current, and that implies this relationship, this equivalent resistance. 15. Same deal here as with 10. I'm just showing you all the different options you have for finding this power dissipated. For resistors in parallel, the easiest option is going to be V squared over R, because I know that resistors in parallel have the same voltage across them. And that's going to be the battery voltage in this problem. So I can find that real quick for each resistor, no problem. It's going to take more work to find current in this case. This is where I would say current is 12 volts over each individual resistance, and then use that to do I squared R or IV or whatever else. So there's usually an easiest equation to use depending on the situation, but there's not a best. There's not one that will work and others don't. You just have to be careful about which current and which voltage. Okay, next 16. All right, a set of light bulbs are connected in parallel to a 120 volt source. In other words, each of these light bulbs has 120 volts across it because they're in parallel. Each bulb dissipates an average power of 60 watts. Circuit has a fuse that burns out when the current in the circuit is 9 amps or greater. Determine the largest number of bulbs which can be used in the circuit without burning out the fuse. So think of each bulb as a resistor, and we can figure out the current driven through them. And since they give us the power of 60 watts, and we know that there's 120 volts across every single one of these, because they're in parallel, that tells me that there must be a half amp going through each, because power is IV, and they told us power is 60 watts. I is the thing I don't know, and V is 120, so I is 0.5 amps for each individual bulb. This question is really just asking how many 0.5 amp currents can I have before it blows out the fuse. Currents in parallel add, so if I have 2 bulbs, I'm going to send 1 amp out from the battery. That's what the bulbs are going to require or draw. If I have 3 bulbs, 1.5. If I have 4 bulbs, it's 2 amps, so on and so forth. At 18 bulbs, that is drawing 9 amps of current. This says the fuse burns out at 9 amps. So I can't have 18 bulbs. I can have 17. I can have one less than what's going to burn out the fuse, but I can't have 18 because that's when we hit that 9 amp limit. That's why it says max safe number of bulbs is 17. Okay, 17. The question is finding equivalent resistance. So this is like that capacitor problem we just did. And I just go step by step of saying what's in series and parallel, what's not. I would say, just based on what I've seen in the past, don't go with your gut. Check, use those tests, or at least just think on it for a little bit before you decide. These might look promising as parallel, or these two might look promising as series, but like with the capacitors, there's reasons neither of those are true. I'm going to leave it to you to double check and understand why on that, because I can tell you about it all day, but you got to practice to make it sink in. For these next steps, it's just recognizing one at a time, or sometimes if I get lucky, there's 3 that stand out like that, and I work until I'm down to 1 single resistor. If you try and do this, just writing out all of the resistance values, like it's 1 over R1 plus 1 over R2, and I got to add that to R1 because it's in, or add that to R3 because it's in series with whatever, you're going to get something wrong. Unless you're just so good at this that you won't, in which case I don't even need to explain to you. So always redraw after you combine resistors is takeaway. 18 and 19. Figure shows a 12 volt battery. What is the current through resistor 2? So this is one where they're asking through a resistor that's kind of bogged down by stuff around it. It's not isolated in a way that it's easy to say what I2 is automatically. So we have 2 options. I usually saved Kirchhoff's rules for when we just couldn't use series and parallel, but that doesn't mean you can't use it when you've just got series and parallel. It's just as good then. So I gave both ways of doing it. You can see that the series and parallel way is shorter, so I would probably recommend it unless Kirchhoff just really clicks for you and series and parallel doesn't. But the idea here is I stop caring what it's asking as soon as I realize it's a problem about finding equivalent resistance, because I'm going to need to know that to find any current in this circuit. To find the current leaving the battery is the first step. So to me, as soon as I read that question, I'm like, oh, find equivalent resistance. Don't worry about what it's asking anymore. And I do that. I work my way down until I find out it's an equivalent resistance of 3 ohms. And that means 4 amps comes from the battery. And then I can work my way back up by just at each stage asking, do I know everything about every resistor in this circuit? If not, there's still work to do. So in this final stage, I know there's 12 volts across the resistor because it's the only thing in the circuit besides the battery. I know the current through it, it's 4 amps. I'm done with that level of the circuit. I take a step back. I know it's 4 amps through both of these resistors because they're in parallel. I'm sorry, they're in series. They have the same current through them in series. And so I can take my answer from here and carry it up. I can't do that with the voltage because resistors in series, the voltage splits. So I have to calculate the voltage. To do that, I use the current, which I do know, and the resistance of each, find the voltage. So it's 6.4 volts apparently for this one. And for the 1.4 ohm, that would be 5.6 volts. Those do add up to 12 volts. That's a good check. They add up to the battery voltage. And then I take one more step back up. And I say, what can I carry up to here? Well, resistors in parallel have same voltage. So I can carry up. In this case, it was the voltage across this equivalent resistance, 6.4. That's true for both, but I have to calculate the current because it splits. And once I've done that, I realize, okay, I know everything about these resistors anyway. What was the question again? What was the current through resistor 2? Oh, well, I already solved for that. I already did all the work by just finding everything about every resistor. So that's my advice. Treat it as the same problem every time, and then look at what it actually asked you for. Okay, 19, same deal. As soon as you know the current and voltage, powers just multiply the two together. So if you found those along the way, just by doing everything for every resistor, you already got every number you need. You don't even have to think. They're already there in front of you. All right, so 26, understanding loops. I'm not sure what else to say for them other than that I always go clockwise. There's never a reason you have to draw your loop any other way than clockwise. It is a choice. You're free to if you want, but it does make it easier to make some math mistakes. So I always draw my loops clockwise, no matter how complicated the circuit. And then I guess the other advice is remember that these signs, the plus and minus, is nothing to do with the loop. It's everything to do with the current. So those signs come from which way you are guessing current is flowing in each part of the circuit. The loops are just a way to say, all right, well, now that I know that, now that I've labeled that, I'm going to report whether I'm walking through rises or drops. And you don't have to solve. So this is the actual cutoff I just did to show you what values we get. And 34 and 35 is equivalent capacitance. So maybe the thing to highlight here is C2 and C3. They don't look quite like our usual parallel because we'd be used to seeing one single wire come out like this. But you can still use the pinch test. Put both fingers on C2 and both thumbs on C3. I can bring my fingers around the wire and my thumbs around, and the only thing I'm going to run into in the middle is a junction. Either if I had drawn it the normal way, like that, I would run into a junction, or with the way it's drawn, this is where I hit the junction. But that's all that's in between my finger and thumb. 35 is once you've found the equivalent capacitance, you just use the idea of what can I carry back to a harder circuit, similar to with resistors. So once I get down to this stage, I know the equivalent capacitance. I can use that to find the charge that's stored on the capacitor. Then I ask myself, if I'm working back up, how did I get down to this step in the first place? I had found that these are in series, which means they have the same charge on them. So that's what I can carry back up. That's how I know these are all 72. The voltage is split, so I have to calculate it. That's what this is. And then I'm done with that circuit. I know everything about each of those capacitors. I take one last step by saying, all right, how did I get from here, this circuit, to this circuit? Well, I had combined these two that were in parallel. What's true about capacitors in parallel? They have the same voltage across them. So I can carry that 6 volts back up. But then I have to calculate the charge on each because that splits. It only happens to be equal in this question because the capacitance is equal. It's not true in general. The charge splits is the only thing that's true in general for capacitors in parallel. Okay, that was the questions that I had gotten over email asking me to clarify. If that still didn't clarify for the people who had emailed, let me know, and I'm happy to talk about it more. But are there other questions?
For the practice exam, number 17, once you get to like the bottom, how are like the last four not in a series?
Number 17. Oh, so right here?
Like the bottom. Oh, yeah, that one.
Yep. Great question. It does look like it up until I notice those junctions right there.
So those are still junctions, even though it's not like.
All a
Like
junction.
what is 1 and 2?
1 and 2 is just some other part of the circuit that we're not told about. It could be that there's a battery, could be all sorts of things going on there, but it's just to say we don't know what's over there. We only know that we're looking off to the side of it and combining these resistances. It's clear in this original circuit, but a junction in general is just 3 or more branches, 3 or more options. And I can see that that is the case here. To show you the currents, think of it as whatever's going on in the other part of the circuit that we can't see. From it, we'll see some current flow into this part of the circuit that we can. I'll call that I guess. Some of that will go this way, but some can go this way. There is a choice, and so those can't be in series. Does that make sense?
Yeah, that makes sense. Thank you.
All right, other questions?
Can you go all the way back to conventional current really quickly and just make a fake example
Yeah.
of when you would need to draw it and the rules, I guess?
So which one?
Like the which way. I put something wrong on that one.
Okay. So for that, let's say I've got a question where I tell you I've got a bunch of electrons flowing this way in a wire, which is the actual thing flowing in a wire. The question would be, which way is the conventional current in this case?
Just the other way.
Yep. So it really is just we're sick of negative charge. We would rather use positive. And in order to be able to do that, we have to pretend it's positive charge moving the other way. So little fake positive charges going this way will accomplish the same thing as negative charge. As far as the quiz question, if I were to word it like that, I think it was something like, which constitutes a conventional current moving south? That would mean positive charge moving south, and I'll just say down is south in this picture. That could either be due to there actually is positive charge moving south, which is not super common for wires. It's usually that there's electrons, or that it was actually electrons moving north, but we replaced them with that conventional current.
So will we always be told like either the flow of the electrons, or like would we alternatively be given like a circuit and we draw the real flow of electrons, or is that not even possible?
So
Uh,
in everything we've done, we have pretty much just drawn the conventional current. All you have to do to get the electron flow is just take every one of those arrows and reverse it. So if I come to like a Kirchhoff's rules one, say all of these were the correct guesses. I don't remember. I think they are. If I come back down. So they all came out positive, it looks like. And so I guess these are the correct actual directions for conventional current. Electrons are actually flowing in this circuit like this, right to left, and around this way, and around like that. And then opposite I2 and opposite I3. So electrons are just doing the opposite of what these pretend positive charges we've been using are doing.
okay, that was it for me.
All right.
Thanks.
Maybe just to remind us why we did conventional current other than um, that we got tired of electrons. So we we know it's electrons. We didn't for a very long time. And so the real reason we came up with conventional current is because that's what we thought was actually happening. We thought it was actually positive charge moving in the circuit. What we eventually found out though was no, it's all those little negative charges, the tiny ones, the electrons. They're what's moving. But we get the same readings for almost everything if we pretend it was positive charge because it doesn't, we get the same answer either way. Negative charge moving one way and positive charge moving the other. That's why we couldn't figure out that it was negative charge for so long. We had to find some physical thing that was different if you had negative charge flowing one way versus positive flowing the other. There is a physical phenomenon where it makes a difference, but none of the ones we've looked at does it make a difference. And so we can always replace electron flow with conventional current for what we've looked at. Other questions?
Can you go through number 2 on the practice exam, please?
Sure. Okay. So, yeah, how about let me draw the circuit for this one. We've got a battery that delivers a current of 3 amps for 12 seconds. To what? I don't know. It doesn't say. So we'll just say some object, some device. Put it in a black box. So our battery sends out a current of 3 amps. That's conventional current that's pretending it's pushing positive charge away from its positive terminal and attracting it towards its negative. But it asks how many electrons that is. So it's asking, okay, but with the thing that's actually going on, these negative charges that are being attracted towards the positive terminal of the battery and repelled away from the negative, how many of them are there in this current? You don't need to know that it's this opposite direction stuff to answer this question, but this is just so you can see that's all that's different between conventional and electron flow. So anyway, how many? Well, if I know the amount of charge that's flowing, how many coulombs, I can say, well, you can fit this many electrons into that number of coulombs. And that's why my first step is to say, how do I relate current to amount of charge? It is the amount of charge flowing per second. So amount of charge itself is amount per second times number of seconds. So I get 36 coulombs flow through this circuit in 12 seconds. And then it's a question of how many electrons go into that charge. How many piles of sand can you put into a big pile of sand if you can only pick them up in little handfuls at a time? You just divide out. You see how many times I can fit the electron charge into the big charge. And that's how I get that number right there. All right. If no other questions, We'll call it there. I will be spending the rest of my day today writing this exam. It's partway there, but anyway, I've written enough that I know what'll be on it. I just have to figure out how to ask it in a different way. So, if you have any questions, feel free to email me. I will get to them over the weekend as well. And otherwise, good luck with the studying, and I'll see you all Monday.